In this video, I am discussing KSET Mathematical Science, Complex Analysis, Previous Year Questions Discussion, Year 2024. Question: the set of all tau belongs to complex number such that series n is equal to 1 to infinity z minus 1 divided by z plus 1 whole raised to n is absolutely convergent is. Options are given. See, we know that radius of convergence, power series radius of convergence 1 by r is equal to limit n tends to infinity. This is supremum modulus of a n plus 1 divided by a n one by r is equal to, or else we simply write limit n tends to infinity modulus of a n divided by a n. R, ORR, another formula is there. Radius of convergence 1 by r is equal to limit n tends to infinity a n modulus of a n whole raised to 1 by n. If we take a n this and apply this formula, we get modulus of this z minus 1 divided by z plus 1. This is in modulus. We can write like this: z minus 1 mod z minus 1 divided by mod z plus 1. This is absolute value. That means we get value, real valued for solving this. That means real of z set of all tau belongs to C such that real of z greater than 0. This is correct option. This is correct option for this question. Next, seventh one. The radius of convergence of the power series n is equal to 1 to infinity 1 plus 2 by n square whole raised to n square zn. Now, we know that formula for power series 1 by r is equal to limit n tends to infinity a n modulus of a n raised to 1 by n. If we apply, this is a n 1 by r is equal to limit n tends to infinity 1 plus 2 by n square whole raised to n square and 1 by n. This n, this 1 n get cancelled. We get limit n tends to infinity 1 plus 2 by n square whole raised to n. Again, this is 1 raised to infinity, indeterminate form. Indeterminate forms. This is indeterminate form. Now apply the formula for indeterminate form. Limit n tends to infinity f of x into g of x. Here f of x, this is f of x. If you apply limit, this tends to 0, and g of x, if you apply limit n tends to 0, we get infinity as n tends to infinity. This is formula f of x into g of x. Now limit n tends to infinity, f of x here 2 by n square into g of x is n. This 1 n cancel, we get, if we apply n tends to infinity, we get e raised to 0. E raised to 0 value is 1. E raised to 0 value is 1. 1 here. Answer is fourth one. This is the right answer. Next, eighth question. If A is in C and R greater than 0, then dash. Options are, there is a number row. This is important. There is a number row greater than 0 such that open ball A to row, open ball infinity A to A row is equal to B of open ball A R. There is a number row such that B infinity A row contained B open ball AR. Next options are given. See concept behind this question. Neighborhood of a point. A set A is a subset of C is said to be neighborhood of Z0. They given row. If there exists an open ball B of R, if there exists an open ball B of R such that this number belongs to B of Z0 R subset of A. Now here this is true in the case of fourth option. Row point, that means number is a subset of this. There is a number row greater than 0 such that B infinity of open ball of B infinity A row subset of B A R is the right answer. Neighborhood of a point, question based on neighborhood of a point. Next, ninth question. If we rotate the point 1 by 2 comma minus root 3 by 2 comma 2015 times about the origin through 60 degree in the clockwise direction, then the resulting position of that point in the place. Resulting position, see, of that point in the plane. They are asking in the plane. They are asking resulting position. This is clockwise direction. Clockwise means negative direction. Rotating in negative direction. See, rotation means it is a map of the form z tends to e raised to I theta into z. Z tends to e raised to I theta into z. Theta belongs to R. This map produces a rotation through an angle theta about the origin with a positive sense. That means theta greater than 0. That means in anti-clockwise direction, and with a clockwise sense, in this case theta less than 0. That in clockwise direction, in a clockwise direction, this is clockwise direction, negative sense. If rotating this is positive sense. Now points are 1 by 2 minus root 3 by 2. We know that tan inverse of y theta is equal to tan inverse of y by x is equal to minus root 3 by 2 divided by 1 by 2. That means tan inverse of root 3 here. We know that in second PU we learnt about sines of theta. Here all angles are positive, all positives. Sine here positive, tan is positive. Here sec and cosec are sec and cos are positive here. Now R is 1. Rotation means f of z tends to e raised to I theta into z. Now f of here e raised to I theta, I phi minus theta. Here what imaginary part is negative. Imaginary part is negative. And this is positive. That means minus theta. Here 1 by 2 plus I plus minus root 3I divided by 2 into z here x plus y. If you remove bracket and multiply, we get this equation. If we take options 1 0, we get 1 by 2 minus I root 3 by 2. That means this option is right one. Minus theta. That means minus pi by 3. See, 10th question. Let f from u to c be an analytic function. Be an analytic function where u as open unit disk, which of the following condition do not imply f is constant on u. F is constant on U. Options are, first one, real part of F is bounded on U. Modulus of F is constant on U. F assumes only imaginary values on U. F dash is constant on U. See, concept behind the question. Result, let F be an analytic function on a domain D, then F is constant. F is constant if any of the following properties are satisfied. That means F of Z is equal to U of X comma Y plus I V of X comma Y. In this case, if U is equal to 0, then F is a constant function. If V is equal to 0, then F is a constant function. Third one, if U is constant. If U is constant, in this case, if U is constant, then F is a constant function. Fourth one, if V is constant, then F is constant function. Fifth one, if F is real valued. F is real valued. In this case, then F is constant. If F is imaginary valued, then F is constant. Seventh one, if argument of F of Z is constant, that means if theta argument of this is constant, in this case also F is constant. Next, eighth one, if image of F lies on a straight line. If image of F lies on a straight line, then F is constant function. Ninth one, if modulus of F is analytic. If modulus of F is analytic, then F is a constant function. Next, if F of Z is equal to U plus IV is analytic on a domain D, and UV lies on a unit circle on W plane. Unit circle on a W plane. If you take, this is a unit circle, value lies on a circle, then F of Z is constant. F of Z is constant in this case also. Now see options. You is unit test, which of the following do not imply F is constant? F is constant. Real part of F is bounded on U. This is true statement. In this case, F is constant. Modulus of F we already saw. This is true statement. F assumes only imaginary values on U. In this case also we get constant function. F dash is constant on U. See, F of Z is equal to Z. If we differentiate, F dash of Z is equal to 1. This is constant, but here F of Z is non-constant. This is non-constant. Non-constant, therefore this is false statement. They are asking for do not imply F is constant on U. Therefore, right answer is fourth one. Next, see 11th question. Let U be a connected subset of C and open in C. Let U be a connected subset of C. C. U is a connected subset of C and open in C. F from U to C be a non-constant analytic function. Non-constant analytic function. Let K be any compact subset of U. Compact means here compact definition says bounded, closed and bounded. Then for any alpha belongs to C, the set Z belongs to K, set of all Z belongs to K such that F of Z is equal to alpha. Here they are telling K is compact. F of Z is equal to alpha is uncountable. Alpha is uncountable. This is wrong. Countable but not finite. See concept. Open mapping theorem. A non-constant analytic function maps open sets to open sets, or image of an open set under a non-constant analytic function is an open set. See here. Here, this is a compact set. We are getting alpha. This is countable but not finite. Countable means empty or a finite. Next, finite. Finite but non-empty. We don't know. This, see, this is true option. Finite. F of Z is equal to alpha is finite. By seeing this statement only, we can arrive this one. Using open mapping theorem, we can easily solve that question. Next, 12th one. Consider the function f from C to C defined by f of Z is equal to Z. Then modulus of f attains its minimum on the boundary B when B is equals. See, minimum. This is concept behind the question is minimum modulus principle and minimum modulus theorem. See, minimum modulus principle. If F is analytic in a domain D and F of Z not equal to 0 for all Z belongs to domain D, then F does not have its minimum value inside D. F does not have its minimum value inside D unless F is constant function. Here minimum value not attained. Only minimum value attained only on the boundary. Next, minimum modulus theorem. See, if F is analytic in a bounded domain D and continuous on boundary with F of Z not equal to 0 for all Z belongs to D. This is important. F of Z not equal to 0 for all Z belongs to D, then F has its minimum value on the boundary of D unless F is constant function. Now see the option. See, if we put the given F of Z is equal to Z, f of 0 is equal to 0. We cannot take this. Here, we want minimum value. Possible values for this is option 3, I 1 by 2. By using statement of minimum modulus principle and minimum modulus theorem, we can arrive options. Not solving manually, we can easily solve by using theorem and principle. See, next, let U is a subset of C. Let U is a subset of C be an open connected set. C is open connected set and F from U to C be analytic. This is open connected set and F from U to C be analytic. Let B is equal to closed ball is a subset of U and M is equal to supremum of set of all modulus of f of z such that z belongs to boundary of D. Then options are given. Modulus of f of z less than or equal to M for all bounded above. For all z belongs to B. Bounded up modulus of f of z less than or equal to M for all z belongs to U. Modulus of f of z greater than or equal to M for all z belongs to B. And modulus of f of z greater than or equal to M for all z belongs to U. See, concept maximum modulus principle. If F is analytic in a domain D, then F does not have its maximum value inside D. Maximum value does not have its maximum value inside D unless F is constant function. Next, maximum modulus theorem. If F is analytic in a bounded domain D and continuous on boundary of D, then F attains its maximum value at the points on the boundary of D unless F is constant function. Now see the statement. F is bounded on the domain D. Here, this function maximum value attains on boundary, but whole function analytic on domain D. Therefore, option 2 is the right answer. For all z belongs to U. See, for all z belongs to F is analytic in a domain D. Therefore, all z belongs to U. Domain here U. Using maximum modulus theorem and principle, we can easily solve the question. 14th one, let phi from C infinity to C infinity be a bilinear map. Let F is equal to set of all z belongs to C infinity such that phi of z is equal to z. Then options are given. One, F is empty. F is non-empty. Second one, cardinality of F is infinite. Cardinality of F is less than or equal to 2. cardinality of F is equal to 2. Now see, bilinear map phi from C infinity to infinity. They given a set F is equal to set of all Z belongs to complex number C infinity in a complex plane C infinity such that phi of Z is equal to Z. They define phi of Z is equal to Z. The complex numbers has at most two solutions because they comes in ordered pair. Z is equal to X plus IY. They comes in ordered pair. Therefore, cardinality of the set F is at most 2. That is, cardinality of F less than or equal to 2. Therefore, cardinality of S is 2. Simple question. Next, 15th one. Let f of z is equal to z raised to 4 e raised to z square for z belongs to C, and let gamma of t is equal to e raised to it. Here t lies between closed interval 0 to 4 pi. Then 1 by 2 pi I integration under the curve gamma f dash of z divided by f of z dz equals. See concept behind this question. Residue theorem. 1 divided by 2 pi I integration under the curve gamma f dash of z divided by f of z dz is equal to n minus p. N here number of zeros, p here number of poles. Now they given t lies between 0 to 4 5. We know that graph of e raised to z, e raised to x or e raised to z is like this. E raised to z, we cannot get e raised to z as 0. Now here z raised to 4 is equal to 0. This implies z is equal to 0. Z is equal to 0 is a 0 with multiplicity. Here multiplicity is 4, and e raised to z square is equal to 0 has no solution for any finite value of z, because e raised to z uh, value for this e raised to z is periodic for value 2n pi I. We get like this. Here they given 0 to 4 pi. This is one time, this is two times. Number of times counter is traversal. That means 1 divided by 2 pi I integration under the curve gamma f of z divided by f dash z is equal to number of times traversed into number of zeros minus number of poles. Here 2 times 2 into 4 minus 0. That means 2 into 4 is equal to 8. See, is there in option 4 8? Option 3 is the right answer. Now this completes your 2024 complex analysis full paper. I think this video is helpful for you. If you like the video, hit the like button. Subscribe this channel for more videos. If you want to practice more questions, join our Telegram group. In that, I post many questions to practice. Link is in the description. Check it once. Thank you for watching.